Hi everyone, welcome back to Core 170. Today we're going to be talking about Bayesian thinking, and if you're not familiar with the concept, sit tight because we're going to learn in a second. And this is going to be one of our mathier lectures. But all that's really required of you is the same thing we've been doing throughout this class, which is you to think critically about the information presented. So we'll start with some opening motivation. Think for a minute about what the word probability means to you. You can press pause on your video, you can keep going, but think about what probability means. And our old friend, the bastion of science, Wikipedia, tells us that probability is the branch of mathematics concerning numerical descriptions of how likely an event is to occur. In your own thought, you might have had some of these: likely and event and occurrence, or how likely it is that a proposition is true. And this definition is pretty good for objective probabilities, things that have an absolute true or false to them. But what about the more subjective decisions that we're going to be making in Core 170? Is there a different way we can think about probability when decisions are more subjective? And in this case, we can think about it in terms of the strength of your belief. Now, for both objective and subjective probabilities, the math of it works similarly. It works the same. Probability in math is a number between 0 and 1 that expresses either an opinion or fact about the likelihood of an event. So a certain event has a probability of 1, and an impossible event has a likelihood or a probability of 0. Now this leads to some truisms that we can draw about probability. One, the entire universe of possible events must add up to 1. The probability of all possible outcomes of a chance event is equal to 1. Put similarly, the probability that an event will occur plus the probability that it will not occur equals 1. Let me say that again. The probability that an event will occur plus the probability that an event will not occur equals 1. So let's use an example from today. The probability that the projector works plus the probability that the projector does not work equals 1. This is the universe of all possible outcomes. Either the projector works or it doesn't work. Now take some time on your own to think about how we can phrase this a different way. And you can phrase it in words, but I'm going to put some math down on the next slide. Different way, the probability that an event will not occur is 1 minus the probability that that event occurs. Take a second to convince yourself that this is true. So let's explore what we know about probability with some trivial examples, and we'll get a little bit more and more complex as the lecture goes on. But in example 1, what is the probability that 1 comes up for a toss of a fair 6-sided die? And notice I'm being very specific here. So we're not, for instance, throwing a 10-sided die. It's not a loaded die. There are no tricks. And of course the answer is 1. 6-sided die, what is the probability that you get a 6 sides to a die? One of those 6 sides has a 1 on it. The probability is 1 in 6. So now let's move on to a slightly more complex example, but still pretty straightforward. What happens when we toss 2 fair 6-sided dice? What is the probability that 2 1s come up? Another word for 2 1s and tossing a pair of dice is snake eyes. So the answer there is 1 in 36. There are now 36 distinct possibilities. We'll explore each of them in a second, and only one of those possibilities is snake eyes. So what happened between example 1 and example 2? We changed the sample space, and what that is the set of all possible outcomes. So in that first example, example 1, there were 6 possible outcomes. It comes up 1, 2, 3, 4, 5, or 6. But in that second example, example 2, where we're throwing 2 dice, there's now a whole new different way of conceptualizing the outcomes. certainly there's that outcome we were talking about, snake eyes, where both dice come up 1-1, but you could have, for instance, the first die comes up 4 and the second comes up 5, the first die comes up 6 and the second die comes up 2, and all in all, there are 36 possible outcomes, and we're interested in one of them. Let's take these probabilities and make them even more complex, just slightly. What happens if we toss 2 fair 6-sided dice? What is the probability that snake eyes comes up if we already know that one of those dice rolls a 1? Now, though this example is more complex, the answer is the same as example 1, 1 in 6. Let's explore how that happens. If we know that one event occurs, we can restrict our sample space to the space of that event under consideration. So in this case, we know that one of the dice rolls a 1. So we're only interested in these gray boxes. And of that, we want to know that both dice roll a 1. So we have, again, 1 in 6. Speaking more broadly, this is something known as conditional probability. It's the probability that an event A occurs, given that event B is known to occur. And we have a formula, a mathematical formula, for figuring this out. So the probability of A given B, this straight line means given, is the probability of A and B, this upside down U means intersection. It's the probability that both events occur, over the probability that event B occurs. Of course, this all is requisite on B not being an impossible event. B being possible, its probability not being equal to 0. So let's explore that with the example of snake eyes. If we know one dice rolls a 1, probability of B, that's the second die rolling a 1, we know, probability of A given B, we know that the second die rolls a 1, is 1 in 6. And the probability of A and B is 1 in 36. Note that we already evaluated these probabilities with examples 1 and 2. Probability B that one die rolls a 1 was example 1. Probability A and B, 1 in 36, was example 2, that you get snake eyes. So 1 in 36 over 1 in 6 simplifies down to just 1 in 6. We see this in the table, we see it in the math, and we have a little graph here to explain it. Now don't pay attention to the fact that A and B are different sizes here, but we're interested in A and B over the probability of event B. There's another way that we can explore this. We can explore it with decision trees. So let me take a minute to explain to you how I wrote this tree out. So we don't have 36 possible branches. I wanted to just simplify it, where we're looking at just a dice rolling a 1 and a die rolling anything that's not a 1, in this case 2 through 6. So on this decision tree, we have a bunch of different paths. We have die 1 rolling a 1 and die 2 rolling a 1. The probability of that happening is 1 in 36. We can also see that that's 1 in 6 times 1 in 6. We have die 1 rolling a 1 and die 2 rolling anything that's not a 1. Probability of that happening is 5 in 36. And again, we can get that by multiplying these branches. So 1 in 6 over times 5 in 6 is 5 in 36. And we see a similar thing on this side, where die 1 rolls anything that's not a 1, die 2 rolls a 1. Since both dice are fair dice, these are the same probabilities. And then we have die 1 rolls anything that's not a 1, and die 2 rolls anything that's not a 1. And that's 25 and 36, 5 and 6, times 5 and 6. There's another way of calculating it, which we talked about at the beginning of the lecture, which is just 1, the universe of all possible events, minus these 3 numbers. These decision trees are important because they help us to visualize these events. So that first example, that one fair 6-sided die rolls a 1, is just this first branch of the decision tree. And if you prefer, we can highlight these 2 branches as well because they're just part of that first branch. So summing the 2 nodes, the end of the decision tree together, 1 and 36 plus 5 and 36, we get 6 and 36, or 1, 6, which is indeed that probability that we came up with for example 1. What about example 2, that both dice come up 1, that you roll snake eyes? That's just the probability that dice 1 rolls a 1 and the probability that die 2 rolls a 1, 1 in 36. And we already calculated that. We've highlighted the whole branch of the tree down to the node. Now, how we exploit probability on these trees is a little more complex. What is the probability that both dice roll a 1, given that you know one die already rolls a 1? So here we have to look at the probability that any die rolls a 1. Or I should say the probability that the second die rolls a 1, which is all the nodes we have highlighted, this probability where both dice come up snake eyes, or the first die doesn't roll a 1 and the second die does. And then from that total probability, anything that happens where the second die rolls a 1, which is a 1 in 6 chance, or 6 out of 36 chance, we isolate the probability we're interested in, that intersection event 1 and 2, that both come up 1. So 1 in 36 over 6 in 36 is 1 in 6. Now that we understand conditional probability, we're interested in something called Bayes' rule, which allows you to find the probability of A given B. Remember, this vertical line means given, and given means knowing that event B occurs, from the probability of B given A. That is, we can invert conditional probabilities. So the probability of A given B is the probability of B given A times the probability of A all over the probability of B. Now that's a little arithmetic, that's a little mathy, but we'll get to the meat of it in a little bit. So let's go to one of my favorite Twitter followers, Roger Sherman, who wants to know, 1, did you attend a college with squirrels on campus? And 2, did people assert that your school's squirrels were in some way different from most squirrels? And let's see if we can't come up with a way to explore Bayes' rule using these squirrels. Because we have a squirrel problem at Sweetbriar. There are 1 million squirrels on the SBC campus, and most are good-natured. But 100 of the squirrels on Sweetbriar's campus are pure evil. And one of my enterprising students in Core 170 has developed an evil squirrel alarm, which she's decided to sell to Sweetbriar for a passing grade. So Sweetbriar, being the robust and studious college that we are going to test her evil squirrel alarm by conducting trials. And what we find in our trials is that when presented with an evil squirrel, the alarm goes off 99% of the time. But when presented with a good squirrel, the alarm goes off 1% of the time. So we want to know, if the alarm is going off, or if a squirrel has set off the alarm, what is the probability that that squirrel is evil? And given the results of that probability, should Sweetbriar buy the patent rights and employ the evil squirrel alarm system? So given what we know about conditional probability, take a minute to try and figure this out on your own before we go over it as a class. So now you should have taken some time to figure this out on your own. But let's go over the math together as a class, because we're starting with some information that we're given. We know that there are 1 million squirrels on campus, only 100 of which are evil. That means that 0.01% of the squirrels on campus are evil. This is what's known as the base rate, the base amount of evil squirrels on campus. Since squirrels can only be either evil or nice, this means that 99.99% of the squirrels on campus are nice. We're also given that when presented with an evil squirrel, so the math way of saying this is conditional on a squirrel being evil, an alarm goes off 99% of the time. This implies is that conditional on a squirrel being nice, an alarm goes off 1% of the time. And what the question asks is, what's the probability, given the alarm is going off, that the squirrel is evil? And remember what we learned about Bayes' rule, the probability of, let's say, x given y, since we have an a for alarm, probability of x given y is the probability of y given x times the probability of x over the probability of a. Or, I'm sorry, y in this case, a for alarm. So, alarm given evil, we have that from the given information, 0.99. Probability of evil, we have that from the given information, 0.0001. So we want to know that the probability of the alarm going off. And we get that from something we didn't discuss, but I'll go over really quickly, called the law of total probability. But basically, the probability of an alarm going off is the probability of alarm given evil, which we're given, times the probability of being evil, plus the probability of alarm given nice, which we're given, times the probability of being nice. Those are the only ways an alarm can go off. Either alarm goes off and you're evil, or an alarm goes off and you're nice. From here, we just conduct simple arithmetic, and it's all given information. So 0.99 times 0.0001 over 0.99 times 0.0001 plus 0.01 times 0.9999, which gives us about 1%. So if an alarm goes off, there's only about a 1% chance of the squirrel actually being evil. And this stems from that base rate, the fact that there aren't that many evil squirrels on campus. In summary, the probability that a random test is correct is 99%. This test is 99% accurate. But the probability that a positive test is correct is 1%. And these probabilities are not the same. In fact, they couldn't be farther from each other. Solve these conditional and Bayesian problems a different way. We can just put them in the table because we're given so much information. So we're given that there's 1 million squirrels on campus and that 100 of them are evil. Since squirrels can only be either evil or nice, we can get the total number of nice squirrels. we're also given that when a squirrel is evil, an alarm is correct 99% of the time. We're also given that when presented with a good-natured squirrel, a nice squirrel, the alarm goes off 1% of the time. Well, we know how many good-natured squirrels there are. So 1% of that is just 9,999, and the rest is just arithmetic. So from here, we know how many times the alarm goes off, 10,098, and we know how many of those alarm setting off squirrels are evil, 99. So it's just 99 over 10,098. Sorry, my E-pen is terrible. And that's about 1%. So if I was Sweetbriar, I wouldn't invest in this evil squirrel detection technology, and I wouldn't give the student a passing grade in Core 170 for developing it. But remember, this is a leadership class. This is not a math class. I'm less concerned with your ability to calculate conditional probabilities as is your ability to think about what they mean for the decisions you make in a data-driven world. So take a minute on your own, maybe text a friend, think about what does this have to do with Core 170. Because remember, we're not just interested in objective probability, things like when you roll dice or published scientific evidence, but we're also interested in your subjective experience. And this rule for conditional probability that we talked about, Bayes' rule, is about revising our probability estimates. In other words, what Bayes' rule tells us is how to update our subjective experience with new information. Let's go back to Bayes' rule and think about what these individual parts, these components of the arithmetic mean. The probability of event A is called the prior, and it's the probability of an event before any new information. So thinking about it from a subjective standpoint, it's our initial degree of belief. How likely do we think it is that A might occur? Which means this second term, probability of B given A over probability of B, is new information. It's the degree of support that B gives for event A. Take a minute to think about why this might be true. And finally, this thing that we're calculating, that we're evaluating, probability of A given B, is the posterior. And it's how we update our beliefs. It's the degree of belief after we learn that event B is true. So if we learn that event B is true, it should update how we feel about event A occurring. Think about those first trivial examples. What's the probability that I roll snake eyes? 1 in 36. But once I've learned that that first die is a 1, the probability of rolling snake eyes becomes much more likely, becomes 1 in 6. And this is important for decisions in a data-driven world, because we don't just have new information or objective probabilities. We also have what we know or what we believe about the state of the world before that new information comes in. And a great way to think about this is in the medical field, where we're not just doing blood work and taking tests and running MRIs and doing biopsies, but we're also taking family and personal medical histories. And we want to know how much that new information, that blood work, changes what we know about how healthy you were before or how healthy your family typically is. So for instance, if I might have some prior probability of you not having a disease, but I get a strange finding on a test, I might update my probability, my posterior, towards you having that disease. Similarly, if you come into my office and you're kind of pallid, have clammy hands, I might think that you have a disease, but when I get a negative finding on a test, I might towards move towards the diagnosis that you don't have that disease. Now, this is kind of a silly example, but it's important to think about what this means for the state of the world, for how we make decisions for Core 170. And really, it comes down to 3 points. Stronger priors, so stronger beliefs, make it hard to update with new information. Alternatively, weaker evidence doesn't update our priors as much. So think about people you know that haven't changed their beliefs or updated at all. Is it because they had stronger priors or because there's weaker evidence? And when we talked on Wednesday about there being lots of bullshit in the world, a lot of it stems from a failure to update our priors, which inundates the world in bullshit. So we have a word for really, really strong priors. And that word is dogma, dogmatic priors. And you might be familiar with the word dogma from not stats, but religion, theology. And certainly you're welcome to have religious beliefs, and if you have that level of faith, then new evidence shouldn't update your priors. But for data-driven decisions, for things where you shouldn't have religious beliefs but be basing them on facts and information, you want new evidence to be able to update your priors. So with that, we'll bring this lecture to a close, and we'll talk about this a little bit more when we review Chapter 8 on Monday.